Hey there, let's jump right into a topic that can feel a little tricky in chemistry, intermolecular forces. We're basically going to figure out what makes molecules, well, sticky. And by the end of this, you'll have the tools to look at different molecules and predict how they're going to behave. Sound good? Let's do it.
So, have you ever stopped to think about this? It's a great question, right? Why is water a liquid at room temperature, but something else, maybe even something heavier, just floats away as a gas? The secret isn't what's inside the molecule. It's all about how they stick to each other. It all comes down to these invisible little forces.
Okay, first things first, and this is probably the most important idea we need to get straight. In the world of molecules, there are two totally different kinds of stickiness going on. One is the superglue that holds a single molecule together, and the other is more like a weak magnet that makes it hang out with its neighbors. So take a look at this. This picture shows it perfectly. See that solid line between the H and the Cl? That's what we call an intramolecular bond. Intra, like within. That's a super strong covalent bond holding that one HCl molecule together. But now, look at the dotted line between the two different HCl molecules. That's our intermolecular attraction. Inter, as in between, it is way, way weaker, but it's the force that decides if you've got a solid, a liquid, or a gas. All right, so let's lock in that definition. Intermolecular forces are just those relatively weak attractions between molecules that are next to each other. They're the glue. If the glue is really weak, the molecules just fly apart. That's a gas. If the glue is a bit stronger, they can slide around each other. That's a liquid. And if the glue is super strong, they're locked in place, and you've got a solid.
So why do we even care about any of this? Well, this is the payoff right here. If you can understand these forces, you can predict all sorts of real-world stuff. You'll know why one thing has a super high boiling point, or why honey is so thick and syrupy. It's kind of like having a chemical superpower.
Okay, so there are a few different types of these intermolecular forces, but we're going to start with the one that every single molecule has, no exceptions. It's called the London dispersion force. Let's figure out a simple way to rank how strong it is.
Think of this as your toolkit. A few things affect these dispersion forces, but for our purposes, we can pretty much figure it all out by focusing on two super simple rules: the size or weight of the molecule and its shape. That's it. These two rules will let you rank molecules like a pro.
Our first rule could not be easier to remember. When it comes to dispersion forces, bigger is better. A larger molecule, one with a higher molecular weight, more electrons, is going to have stronger forces. Simple as that. And you don't have to take my word for it. Just look at this chart. This is the proof right here. See the halogens in blue? We start with tiny fluorine, F2, with a boiling point way down at 85 Kelvin. Then you jump to chlorine, Cl2, at 239 K. Bromine, Br2, is up at 332 K. And then look at iodine, I2. It's all the way up at 458 Kelvin. As the molecules get bigger and heavier, their boiling points just skyrocket. That is a direct result of stronger London dispersion forces. All right, let's move on to rule number 2. Now, this one's a little more subtle, but it is just as important. When you have molecules that weigh the same, their shape is what makes all the difference. And this is the perfect example. Check this out. N-pentane and neopentane have the exact same formula, so they weigh exactly the same. But N-pentane boils almost 30 degrees hotter than neopentane. So why? Just look at their shapes. N-pentane is long and kind of dangly, while neopentane is all balled up. Think of it like Velcro. The long N-pentane molecules are like two big strips of Velcro. They have a ton of surface area to stick to each other. Neopentane is like you crumpled those same two strips into little balls. They can barely touch. More contact means stronger forces. Okay, theory time is over. You've got the rules, now it's time to actually put them to work. I'm going to throw a couple of questions at you. Let's see if you can figure them out. First one up, bromine versus iodine. Which one has the higher boiling point? Think back to rule number 1. Which one is bigger? I'll give you a second. If you said iodine, you are absolutely right. Nice job. So why is it iodine? It all comes back to that first rule, right? Iodine is way down on the periodic table compared to bromine, which just means it's a bigger, heavier molecule with a lot more electrons. That all leads to stronger attractions between the molecules, so you have to crank up the heat to a much higher temperature to get them to break apart and boil. Okay, ready for question number 2? Which one has stronger dispersion forces, N-pentane or neopentane? This one is all about rule number 2.
And the answer is N-pentane.
So what's the logic here? Well, since they have the exact same mass, we have to look at their shape. And the long, stringy shape of N-pentane means it has way more surface area to make contact with its neighbors. It's that Velcro effect we talked about. More contact equals stronger dispersion forces. It's as simple as that.
Excellent work. Okay, let's pull all of this together for the big aha moment. What is the one key idea you absolutely have to remember from all of this? This quote really says it all. Everything we see on a big scale, like ice melting or water turning to steam, it's all controlled by the strength of these tiny invisible forces. If you can master these forces, you can understand the states of matter.
So, I'll leave you with this question to chew on. Think about why oil and water don't mix, or why some paints are thick and others are runny. It all comes back to these forces. Now that you know the rules, I promise you, you're going to start seeing their effects everywhere. So keep looking and keep asking why.